So, good evening, students. So, we in the last class we completed continuous system for one-dimensional problem. We considered the string, rod, portion of vibration, and also the beam transverse vibration. In continuous system, one more aspect is left out that we'll consider toward the end of the semester. That is two-dimensional problems. That is, one is the membrane and another is the plate problem. So depending upon the time, or at least the membrane problem we'll try to cover. Plate problem I will introduce, and then the detail of the formulations I will not able to cover, I think, within the time frame. But I'll introduce the membranes in more detail because there the equations become more in number, and for simple boundary condition we will able to solve that. So in the previous class I started something on the continuous system. The enclosure theorem I explained. Now we'll see the Rayleigh's quotient today, and then we'll switch over to the approximate methods, especially for the continuous systems. There are several approximate methods for finding the eigenvalue problem, and those approximate methods will maybe halfway of this today's lecture will start. But this Rayleigh's quotient is also in a way this approximate method. So we are now switching gradually toward the approximate method because the solution for the continuous system, especially when the geometry is complex and the boundary conditions are more complex, then the solution becomes more cumbersome. And only way we can able to get some approximate estimates of the natural frequency is the approximate method. And so I will share the slide for the Rayleigh's quotient. As we discussed in the case of discrete system, the similar concept is there, but the eigenvalue problem is different. So this is the Rayleigh's quotient for continuous system. So this is the eigenvalue problem we discussed, in which this is a general eigenvalue problem where M and L operator lambda is the value, or W is the eigenfunction. So, and we have been talking about this general eigenvalue problem for continuous system. Basically, this represents even for the two-dimensional problems also. And we have seen that the L operator is having 2p order of differentiation in general, and M is having 2q, where p is greater than q. And if we have eigenvalue, if we are taking one of them as lambda r, rth eigenvalue, and associated eigenfunction, if we are saying wr, then if we substitute in this, they should satisfy the equation. So if we substitute this rth eigenvalue and eigenfunction, this it will satisfy this equation, and r can take a value from 1 to any value up to infinity. So, and now what we'll do, we'll multiply this particular quantity both sides by eigenvalue, eigenfunction wr, both sides, and then we'll integrate over the domain. And then once we integrate, we'll take this quantity, will divide both sides. So basically, we will get the equation. We multiplied the previous expression by wr, both sides. We integrated over domain, Then we divided the right side quantity except that lambda r. So we got this ratio. So obviously when these functions are eigenfunction, we get the eigenvalue of the system. So this is coming from the eigenvalue problem where we are considering the operators are self-adjoint. The symmetry nature is there in that. Now, if this eigenfunction, because to get the eigenfunction, we need to solve the eigenvalue problem first. But before solving the eigenvalue problem, whether we can have some approximate value of the eigenvalue, that is the aim of the Rayleigh quotient. So now we are directly assuming this eigenfunction in the form of comparison function. So comparison function is having less requirement as compared to the eigenfunction. Comparison function's requirement is that it should satisfy both all the boundary conditions of the problem, geometrical as well as natural boundary condition, and it should be differentiable up to 2p. That is the requirement when we choose the comparison function. So in the previous class, we have seen how we have chosen the comparison function. So that choice is always arbitrary, but we need to ensure that the boundary conditions are satisfying. Through one example, we'll see this comparison function in the subsequent slide. So if we choose the comparison function u instead of w, so the equation will be like this now. So in place of wr, we are writing the comparison function u, and u is a uh, approximate eigenfunction, I can say. So obviously, if it is approximate, the ratio will not be equal to eigenvalue, but that ratio we are calling as a Rayleigh quotient for continuous system, and the square of that is equal to the square of the natural frequency, approximate natural frequency. And this when we have the for positive definite system, this ratio is always positive, so that when we take the square root of this Rayleigh quotient, we will get the real eigenvalues or the real natural frequencies. Now the comparison function will be having of this form in general. So this is you can see that u is having a summation of some constant and wi, where wi is a eigenfunction in more general way. So this is the Rayleigh quotient. We'll see how this can be approximated. Now we are taking more number of terms in the eigenfunction, this comparison function. Now we'll see if we substitute this. Okay, so before substituting, let us see some of the property of the M operator, which we have been deriving in the previous lectures. So this is the normalization of the eigenfunction, ith eigenfunction with respect to the M operator. And if this wi are different, wi and wj, then this will be 0, and that we represented by Kronecker delta ij. The property of this is when I is equal to j, then its value is 1. So that is satisfying this. If I and j are not equal to 1, then this will be 0. So that is the orthogonality condition. Similarly, for the L operator, if we take the same eigenfunction, we get the eigenvalue. And if we take the different I and j, then that can be represented like this, where if I is equal to j, this will be 1, so that will be equal to this expression. Otherwise, it will be 0. Now, this property will be using. So here I'm coming back to the Rayleigh quotient which we defined. let us see the comparison function u, which we have chosen here, which is in the form of the eigenfunction. So if we substitute this here instead of u, you can see this is the thing we assume CIWI, and then L operator in place of u again we're substituting that particular series and integrating over the domain. Similarly, in the denominator we are putting u as that series and then M operator and the series. So now next what we are doing, because this integration and the summation operator we can able to interchange. So what we are doing, we are keeping the summation outside and bringing the integral inside. So you can see summation with respect to I, summation with respect to j. Ci and Cj are constant, so they are coming out from the integration, and whatever is left out is Wi and L operator Wj d, capital D. So this is the rearrangement of this expression. We have taken out the summation. Similarly, in the denominator, we have taken out the summation outside. Ci's and Cj are constant, so their integration over the domain. Domain is for one-dimensional, it will be dx only. For two-dimensional, it will be dx and dy. So that's why this particular expression has been written in the more general way. So it represents for one-dimensional also and two-dimensional problems also. Now, if you see this expression, according to this will be lambda I delta ij. This can be replaced by that. Similarly, this can be replaced by using this expression by delta ij, where delta is the canonical delta. Now, if you substitute that, we'll get Ci, Cj, lambda I, and delta ij. Similarly, here only delta ij will be there. Lambda is not here. And now, because of this property, because if we operate this operator, what we'll find that whenever the I is not equal to j, this will make that particular term 0. Here also, when I is not equal to j, this delta ij will make that particular term 0. So only those terms will be left out in which I is equal to j. So we'll be having such terms. So here when I is equal to j, so this will be Ci square, and here it will be Ci square into lambda I. So now if you remember, the Rayleigh's quotient for the discrete system was having the similar form. Only thing was the number of terms there was n. Now here, because of continuous system, whose degree of freedom is infinity, we have infinite number of terms. Otherwise, this is exactly similar form as the discrete system. So you can see that if we are truncating this series up to n, so that means we are approximating the continuous system as a discrete system in some way. So that is the analogy between the this continuous system and the discrete system. Rayleigh's quotient is there. So here, in getting this, we have applied the orthogonality condition of the eigenfunction to get this expression. Now, the property of this Rayleigh's quotient, that is always greater than or equal to the fundamental eigenvalue or the first eigenvalue of the continuous system. So that whatever was there for the discrete system is valid here also, that it gives the upper bound for the lambda 1. Lambda 1 is the lowest eigenvalue of the problem. Now, okay, so now, because now what we are trying to do, as we have done for the discrete system, let us say we are choosing the comparison function which is not containing the first n-1 eigenfunctions. So whatever the series we discussed earlier, this series, so we are not taking the I is equal to 1 to n-1. So we are starting from I is equal to n to infinity. So that means first n-1 eigenfunctions are not there. Let us say whatever the comparison function we have chosen. Then what will happen? If this comparison function is not containing the first s-1 eigenfunction, then according to the orthogonality condition, what will happen? This will be 0 because wi I is 1 to s-1. So they will be 0 because they are not there in the U. So U is not containing sth s plus 1th eigenfunctions. So they will never be equal to wi. So I is from 1 to s. So whatever the terms are there in the U, because starting with the s, ws plus 1, so that will never be equal to wi. So that's why according to the orthogonality conditions, we'll be getting this term as 0. So this I already explained that in the chosen eigenfunction, the comparison function, sorry, we are not choosing the first s-1 terms. Then we are trying to see how the Rayleigh's quotient will take the form. So that means in that particular case, the Rayleigh quotient will predict the ratio will be either equal to the sth eigenvalue or more than that. So this we already seen in the discrete system also, that if the chosen eigenvector there is not containing the lower s-1 eigenvector, then it will predict the eigenvalue either equal to the sth eigenvalue or more than that. So this is similar to the previous as we have discussed in the discrete system. Now we'll take up one example. So here there is a continuous system. There is a axial rod which is vibrating axially. There is a cantilever rod. Here this is the x is equal to 0 where displacement is 0, and this is the x is equal to L where the axial force is 0. So EA and du by dx at x is equal to L will be 0 here because there is a free end, so no axial force will be there at the free end. Now we are choosing a comparison function. So here you can see the choice of the comparison function is this. Now what is the requirement of the comparison function? That it should satisfy the geometrical condition and the natural boundary condition. So what is the geometrical condition here? Geometrical condition is when x is equal to 0, u should be 0. So this is the geometrical boundary condition. So if you put here x is equal to 0, is becoming 0. So it is satisfying the geometrical boundary condition. The natural boundary condition at x is equal to L, this derivative of this u should be 0. So if we take the derivative of the u, so u prime is representing the derivative with respect to x. So if we take the derivative, we'll get this expression. Now, if we put x is equal to L here, we'll get 3 by L here minus 3 by L. So this term will be 0. So this natural boundary condition also, this comparison function is satisfying. So there can be different functions we can choose. So initially it will be difficult to guess, but as we will get familiar with the functions, this polynomial especially, okay, how to rearrange this so that you can able to satisfy this kind of boundary conditions, then we can able to choose this. So this is arbitrarily chosen, but it is satisfying the boundary conditions of the problem. Now, to get the Rayleigh's quotient, we need to, Rayleigh's quotient is defined as this. So we need to operate the chosen comparison function with the L operator. Then we need to multiply by U, and then we need to integrate. Similarly for the M. So that operations we will be doing it. So step by step we'll do. So first we'll apply L operator to the U. So L operator for the beam case is, the cantilever axial rod case is minus EA del square by del x square. So when we apply the U operator, U to this L operator, we will get this. So we'll differentiate this twice. So we'll get this expression. Similarly, M operator is for the axial rod case is only rho. So here there is no differentiation required. Just this function multiplied by rho will be the MU. So now we have obtained L, which we operated to the U, and M operated to the U. Now we'll integrate it. So now we are multiplying the U with this LU and integrating over the domain. Here domain is X, one-dimensional X only. So here you can see that U and this, we already obtained this earlier. I'm not given all the expressions here. So this into this, if we integrate, so you'll get this kind of expression. Similarly, when we integrate U into MU was rho and that expression. So if you can see, we're getting the square of the term here because U square is becoming here, so that is the square of that. And yeah, so if we integrate this polynomial, we need to expand it, then integrate, and then put the limits. So all those expressions, simple integrations we need to do, and we will get this as a this integration. So here simple integrations are there, definite integral. We need to integrate and then substitute limit 0 and L here also. So, and then once we have got this, we can substitute this and this here. So we will get, after simplification, the Rayleigh's quotient like this, or after simplification we will get this. So if we take the square root of this, then we can able to get the natural frequency. So if we have already solved this axial rod case in the closed form solution, the exact value of this we already solved by solving the eigenvalue problem and like that. But here directly from Rayleigh's quotient we are trying to predict. So the lambda, we got this expression. The coefficient is 2.4706. From the previous closed form solution which we obtained, the first eigenvalue was 2.4. So if you compare these two, this is the exact value which we should have got if we have chosen the comparison function as eigenfunction. But comparison function is a approximate function, so there is some deviation between the coefficient. So but the difference is in the second decimal only. 2.4 is okay. 6, 7, here 70. So difference is there in the second decimal. But if you compare, the Rayleigh's quotient is higher than the actual one. So that particular condition which we were saying, this kind of condition, Rayleigh's quotient either gives equal to or greater than the first natural frequency, that we are able to satisfy here using this. So here, while obtaining this, we have not solved the eigenvalue problem. We have chosen a function we can have different choice of this. We have chosen this one function, but we can have different choice of this also. And just we substitute that function in the Rayleigh's quotient, which involves the differentiation and the integration as per the axial vibration problem, and we got the natural frequency. So, and this has been obtained using the proper eigenvalue problem formulation. So you can see that quite close value we could able to predict using the Rayleigh's quotient if the comparison function is satisfying the boundary condition, both the boundary conditions for the problem. So this is regarding the Rayleigh's quotient, which I discussed. So I'll start with the next chapter. But if you have any questions, I can take up any questions if you have. Otherwise, I will go for the next chapter. That is also approximate method. But there we'll not only try to find the first natural frequency, but even the higher natural frequency also can be obtained. So, okay, so I will start the next chapter. So here we'll be focusing on the natural modes, finding the natural modes, natural frequency, and either eigenvector or eigenvalue. So these methods will be applicable for both discrete system as well as the continuous system. For both, we'll cover this, and yeah. So especially when in the continuous system, these methods will be very useful. Especially, we have seen that whatever the solution in the last chapter we have obtained for continuous system, in which the beam was uniform, the cross section was not varying, the boundary conditions were simple boundary conditions, either fixed end or free end or simply supported, that kind of boundary conditions. When we had the boundary conditions of the spring attached at the free end or the disk attached at the free end, then the eigenvalue problem became more complex. So whenever there is a non-uniformity of the geometry and the complex boundary conditions are there, then such closed form eigenvalue problem is not feasible. It becomes very complicated. So we need to resort for some approximate method. And approximate method, actually, what it does to the continuous system, it converts the continuous system having infinite degree of freedom system to equivalent discrete system. So equivalent discrete system. So as we have seen in the Rayleigh's quotient, if we truncate the series from infinite to some discrete value, there is some correlation between the continuous system and the discrete system. So this equivalent discrete system will be exactly same as continuous system if we have the discrete system as having degree of freedom infinity. So that is the limit. So if we discrete system, if we have gradually, if we are increasing the degree of freedom of the discrete system to infinity, the whatever the eigenvalue and eigenvector will be getting, or the eigenfunction will be getting from discrete system, will be equal to the continuous system. Okay, so here, as I mentioned, all the methods which we'll be dealing with, the continuous system will be discretized to n degree of freedom system. In the Rayleigh's quotient and in the enclosure theorem, we never talked about the degree of freedom. Only we wanted to enclose some natural frequency. Even we don't know which in natural frequency we are enclosing it. it depends upon the choice of the eigenvector we have chosen, or the comparison function we have chosen. So now, based on the Rayleigh's method, Rayleigh's quotient, we more systematically will be developing the method which can discretize the continuous system to a n degree of freedom system, and so that is the basic crux of the approximate method. Okay, so first one is the energies and Rayleigh's energy method. Here also, this is actually one step ahead of the Rayleigh's quotient, and here previously in the Rayleigh's quotient we use the, especially when we are talking about the continuous system, Rayleigh's quotient we define in terms of the L operator and M operator. Okay, so but in the energy method, we'll try to write the Rayleigh's quotient in terms of the energy itself, because from energy we obtain the equation of motion, and equation of motion defines the L and M operator. So here we are, rather than going to L operator and M operator, directly we'll be using the potential energy and the kinetic energy of the system to obtain the some estimates of the natural frequency. Here also we are focusing on the initially for the only the first natural frequency. Maybe in the next class we'll extend this particular method for the more degree of freedom systems. So here when we are talking about conservative system, when it is vibrating about the equilibrium position, because we have the frequency which is always, we assume that the natural frequency is when the system is vibrating with its natural frequency, there is always harmonic, and at equilibrium position during the vibration, this natural frequency is having the stationary value, and corresponding stationary value means the either it will be minimum or maximum, but here the stationary value at the neighborhood of the fundamental mode, when we are talking about the first mode, this will be minimum, the stationary value of the this particular. So basically stationary value itself will be the frequency of oscillation. So I think this will be more clear as we go for the expressions of these. So yeah, coming to the discrete system. So first we are considering the discrete system. So here you will find that initially I'm discussing again the discrete system. Maybe 2-3 lectures I'll talk about the discrete system. Then I'll go for the continuous system. So now this Rayleigh's energy method I'm describing for the discrete system again. So if we have, let us say, n degree of freedom system, discrete system. So forget about the continuous system now. We're not talking about the L operator, M operator. So the generalized coordinate is Q. Qi is, so I can vary from 1 to n. So we generally express the generalized coordinate as the amplitude and the harmonic function. And because there are any number I is varying from 1 to n, these can be combined in a vector form. So this vector is a column vector of n into 1, and this is also column vector of amplitude n into 1. Now the kinetic energy of the system is expressed as this, because the motion is harmonic. So the velocity terms, if we substitute this, because this is a time dependent function, so derivative, the dot is representing the derivative. So one f dot will come from here and another will come from here. So that will make f dot square. Dot is the derivative with respect to time. So this is the kinetic energy of the discrete system. Potential energy we write like this, in which when we substitute in this form, so this time function will come out. So basically, kinetic energy and potential energy we write in terms of the generalized coordinate. Generalized coordinate we have expressed in the amplitude and the time function form. So they are taking this form because one f will come here, another will come from here. So that will be f square, which is function of time. So this is the kinetic energy and the potential energy expression. Now, in a system, any conservative system, we know that let us say the pendulum that is when it is oscillating, this is one of the extreme. So what will happen after this? It will return back to the during the oscillation. So here, once it is returning, that means for the extreme position, the velocity of the pendulum is 0. So velocity is 0 here. When it is coming here, this is the bottommost position of the pendulum. So here we can expect the velocity will be maximum, but now the potential energy will be minimum. So if we are considering this and these two positions of the this particular bob, so here we'll be having potential energy 0 plus kinetic energy will be maximum. At this position, we'll be having potential energy maximum, but here the kinetic energy will be 0. And we know that in conservative system, the total energy, the potential energy and the kinetic energy at any particular point are equal. So this both will be equated to a total energy of the system. So that is giving us a relationship that the maximum kinetic energy of the system will be equal to the maximum potential energy of the system, which are taking place at this location and this location respectively. Now, if the ft is harmonic, then this first derivative which we had earlier, so that we can able to write it as omega square, because f dot will give us the omega f, and f is, so if we are using f t as a, let us say, cos omega t or sin omega t, which are harmonic functions. So if we take the derivative of that, that will get the omega square from that. If we take derivative, 1 omega will get, and the square is there, so we'll get the omega square, and the cos will be having maximum value 1. So basically, because we are interested in the maximum kinetic energy, so that function maximum value will be 1, so that we have taken. So, and this T star is defined as without the omega. Without omega is the T star. Yeah. So this is the, so T star is some kind of a reference kinetic energy we call this. So omega square is excluded from this expression. Maximum kinetic energy is T star omega square, and T star is the remaining term. Similarly, the potential energy V maximum, because function ft is, let us say, cos omega t, and then the maximum value of that will be 1. So that has been equated to 1 to get the maximum potential energy. Now we are equating these two, maximum kinetic energy and potential energy, from previous. So omega square T star and Vmax. So omega square can be written as Vmax by T star. Omega x we represented in terms of the stiffness matrix. T star we represented in terms of the mass matrix, because this is the kinetic energy. So this is the Rayleigh's energy expression. So you can see earlier we represented differently the Rayleigh quotient or the discrete system. Now we are represented using the energy. So these are the energy terms. If we go back to the continuous system, we represented the Rayleigh quotient in terms of the eigenvalue problem. So, but here in the subsequent lecture, we'll see the similar Rayleigh quotient using the kinetic energy and the potential energy will be deriving for the continuous system, but this for the discrete system. So now this Rayleigh quotient, energy quotient, if we are using U as, let us say, first eigenvector. So if we use first eigenvector, we expect this ratio will be equal to the first eigenvalue. So that is, and if U is not same as the first eigenvector, then this ratio will be always more than the first eigenvector, as we had the condition for the Rayleigh quotient, because it gives always the upper bound of the first eigen value, this particular ratio. Okay, so now through one example, we'll see how this Rayleigh's energy method works. So here we have a discrete system in which, let us say, because we are already familiar with if a system is given, how to obtain the equation of motion, how to obtain this stiffness matrix, mass matrix. So those things I'm not repeating. Directly I'm giving, let us say, this is the stiffness matrix for a particular system. This is the mass matrix given to us, and we want to use the Rayleigh quotient to obtain the fundamental natural frequency or any other natural frequency which we can get. So here we have chosen some arbitrary vector, let us say u1, u2, u3. So we have chosen the non-zero, as we have done previously also using the Rayleigh quotient. So we have chosen some arbitrary vector 2, 3, 2. You can observe that all the terms are having same sign we have taken. So we expect that whatever the estimates will get will be closer to the first natural frequency. Also, none of them should be zero because we will be taking the ratios, and so whatever the terms we are taking should always be positive. So case one, in which we have chosen this particular eigenvector as a approximate eigenvector. Now we need to obtain the Vmax. Vmax is stiffness, and this is a column vector, this is a row vector of the same thing. So you can see row vector is 2, 3, 2, 2, 3, 2, and this is the column, and this is the stiffness matrix which is given to us. Now if we multiply this step by step, we'll get 14 Gj by L. Vmax is this much. Similarly, Tmax star will be mass matrix, and U and U vector is multiplied pre and post. So if you do the multiplication, we'll get again this has 21 ID. So we got the Vmax and Tmax star. Now we can obtain the ratio of that. So the ratio of this is Vmax Tmax. So we obtain this, and if we simplify, we'll get this. And if we take the square root of this, we'll get the natural frequency of the system. And if we simplify, we'll get this is the natural frequency of the system. Now, because this is a discrete system, we can check how close this value we have approximated with the eigenvalue problem with the eigenvalue problem solution. So this particular solution is from the eigenvalue problem, which we discussed in the chapter 4. And in fact, this particular example has been solved using eigenvalue problem in example 4.3. So the first natural frequency of that particular system is this much. So now if you compare these two, you'll see that the approximate natural frequency is more than the actual one. That is the Rayleigh's quotient condition, and this is close to the first natural frequency. And always the Rayleigh's quotient over predict the natural frequency, the fundamental one. Here we chose the eigenvector all positive, and we got this much closer. Now the same eigenfunction, we are slightly fine tuning it. So 232 was there, now 2.4 to 3.2 and 2 we are resuming. So again I'm obtaining with this Vmax, I got this P star max, I got this. If I divide this to I got the Rayleigh's quotient, and if I take the square root of this, I got this value. So now it is 0.8124. The exact value is 0.820. So is now further closer to the actual value. Previous was 0.865. So here difference was more. Now with this we got much closer to the actual value, but still is higher than this, which is the condition of the Rayleigh's quotient, that is always overpredict the fundamental natural frequency. So this is one. Now I'll take another arbitrary vector. Now I'm taking one of them as negative because I'm going closer to the second eigenvector by taking negative. So here, as we have done in the Rayleigh's quotient also earlier. So with this again, we will calculate Vmax, T star max, take the ratio, obtain this, and if you take the square root of this, I'll get the natural frequency. So this is the natural frequency I'm getting, 1.3452. So of course this is not close to the first natural frequency, but this, if we solve the eigenvalue problem, the second natural frequency is 1.2957. So now it is closer to this and higher than that, because this is not this is a very approximate value. So the difference is much, but this can be fine-tuned to get much closer to this. So I'm leaving it to you to fine-tune and check this. So this is regarding the case 3, in which we have taken one of the eigenvector as negative, component is negative, so that it is closer to the second natural frequency. Now I'm taking, so when I'm taking negative here, so what is happening, this and this are having synchronous mode and this is having opposite motion. So that is the characteristic of the third mode, which we have seen earlier also. So with this eigenvector, if we again obtain Vmax, Tmax, and divide them and take the square root to get the natural frequency. So we have here 1.7183, and the third natural frequency of the same system is 1.7781. So now you can see this is closer to this, but what is happening now, it is less than the highest natural frequency. So this we already know that according to the enclosure theorem, always the prediction will be less than the maximum natural frequency. Is more than for the fundamental natural frequency, but for the maximum natural frequency, prediction will be less. So that is, we are able to check that. It's quite close, but still this is less than this. So for highest natural frequency, the third natural frequency, we get the lower bound from this Rayleigh's quotient. So here, because you must have observed here, repetitive multiplications are there. So best is if we can have small code like this in MATLAB or Scilab, like if we define the K matrix and then mass matrix. So here, in fact, I solved the eigenvalue problem completely. Then I have used the Rayleigh quotient and other things. So here I'm taking the m divided by k. Then I'm solving the eigenvalue problem. Then I'm obtaining the natural frequency by square root of that. And then these are the eigenvector normalization. And here I'm using the Rayleigh quotient. This is not enclosure theorem, this is a Rayleigh quotient using the energy method. So you can see that the same K matrix post multiplied by U and pre-multiplied by transpose of U. 2, 3, 2 we have assumed. Prime represent that it should become column vector, and similarly W. So this is Vmax, this is Tmax, and then there's the quotient ratio Vmax and W, and we take the square root of that, we'll get the this all the natural frequency. So this is similarly we can try out different eigenvector -2, 3, 2, -3, 2. So these are repetitive calculations can be done here. So we'll get directly all the calculations like stiffness matrix, mass matrix, this D matrix which you define is the eigenvector first, second, third. So according to this, these are the eigenvalue. So this is the lowest. So this is the corresponding to that. You can see all positive. This next. So here you can see two are having same sign. One is opposite. Here third, this middle is having opposite as compared to that. So these are the natural frequency and corresponding mode shapes for the eigenvectors. And if we take the square root of this, we'll get the natural frequencies. So this is the fundamental natural frequency 0.8, 1, 2, 3. So these are from the actual eigenvalue problem. And then we use the eigenvector, approximate eigenvector 1, 2, 3, and we use the energy method to get the natural frequency. So, and the comparison, whatever the calculation has been done, has been shown here. So this is from first, second, and third, and we can compare this with the exact one. So this for the discrete system, the code is there, simple code, but all repetitive operations can be avoided. Especially for bigger problems, this will be very helpful, because here we can define any K matrix and mass matrix of any size. This will give all the calculations because all of these are in the variable form. So I'll encourage if you have the facility for writing the code and the assignments, try to submit. Otherwise, no issue. You can do the same thing with the hand calculation also. So with this, I will stop here. And if you have any questions, we'll ask. If you have any questions. Okay. So no questions. So we have quiz on 2nd November. So that I will take on the mainly the chapter 5 continuous system, whatever I covered, including the Rayleigh quotient and enclosure theorem, the Rayleigh's energy method. The chapter 6 thing will not be there, but prior to that, the continuous system, I will take the quiz on 2nd November during the class timing. And if you have, okay, then so good evening, and stopping here now.